All right, good afternoon. We are talking about 8.2, the law of cosines. If you want to know the derivation or where the law of cosines comes from, you can check out the PowerPoint posted on Schoology. But for time's sake, we're going to skip down to the actual law of cosines. So in any triangle ABC with sides A, B, and C labeled as normal, where angle A is directly across from side A, then the law of cosine says that a squared equals b squared plus c squared, which looks pretty similar to the Pythagorean theorem, but when we add in this minus 2bc cosine of A, that allows us to use any triangle to find any side length if we know two sides and the angle across from the side that we're looking for. Okay, and you can rearrange and do any combination. So the square of a side of a triangle is equal to the sum of the squares minus twice the product of those sides and the cosine of the angle A between them. Okay. So if we take a look at this, this allows us to use more than just the law of sines to find missing sides, but also the law of cosines. And this is a extension of the Pythagorean theorem. So a surveyor wishes to find the distance between two inaccessible points A and B on opposite sides of the length. So they cannot get to these points to be able to directly measure them. But while standing at point C, she finds that B is equal to 259 meters, A is 423 meters, and angle ACB measures 132 degrees and 40 minutes. And we want to find this distance C. So in order to do this, we are trying to find C, so we're going to use the C squared version. So this is A squared plus B squared minus 2 times A times B times the cosine of angle C. So C squared is 423 squared plus 259 squared minus 2 times 423 times 259 times the cosine of 132 degrees and 40 minutes is going to be 132.67 degrees, because 40 minutes is 2/3 of a degree. And when we plug all of this into our calculator, we're able to get that C squared is approximately 394,510.6. And when we take the square root of both sides, we can see that C is approximately 628 meters. Okay, this is most useful for being able to measure and survey for those of you interested in engineering. Okay, we can also do this even when we don't know what the triangle is going to look like, but we can do a rough sketch of triangle ABC. So here we have triangle A, B, C, and angle A is 42.3 degrees, side B, A, C, B is 12.9 meters, and side C is 15.4 meters. And remember, to solve the triangle means to find every other side and angle that we don't know. So what we know the most about are the sides. Now you could use law of sines or cosines, except we don't have two angles, and that becomes a little bit more tricky to do. But we can find A squared equals B squared plus C squared minus 2 times B times C times the cosine of angle A. And we have B, C, and the angle A. So A squared is 12.9 squared plus 15.4 squared minus 2 times 12.9 times 15.4 times the cosine of 42.3 degrees Make sure your calculator's in the correct mode. And when you take the square root of all of that, you can even do the square root in your calculator around everything. A is approximately 10.47 meters. And then with this, we have to be a little bit careful in that we have a side, an angle, and a side. And B is less than C, which tells us that B has to be less than angle C, which means that it's not going to be obtuse since it also is going to have to be less than angle A, because angle A is the shortest of the sides. Okay, so even though C is going to be the greatest, it's the only one that has the possibility of being obtuse. B definitely cannot be obtuse. We can then use the law of sines to find the measure of another angle now that we have all three sides. So if we wanted to find angle B, we know that the sine of A over A equals sine of B over B. We're doing sine on top because we're looking for angles. So sine of 42.3 degrees over 10.7 equals sine of B over 12.9. When we multiply both sides by 12.9, we get that the sine of B is equal to 12.9 times the sine of 42.3 degrees over 10.7, and we can put all of this into inverse sine. So when we inverse sine both sides of that, then we get that B is approximately 56 degrees. So here's one of our things we're looking for, here's another, and now that we know two angles, now we can find angle C is 180 minus angle A minus angle B. And so C is going to be 81.7 degrees. This becomes another formula that you will need to know. The good news is once you know one of these, you can easily rearrange to get the others and you just swap out. All right, try example 3 on your own or check your answer with a buddy and then click play to check your answer. All right. So for this one, we can find the measure of the largest angle C. If the cosine of C ends up being less than 0, then the angle C is going to be obtuse. So we know C squared equals A squared plus B squared minus 2 times A times B times the cosine of C. Since we know all three sides here, we can rearrange to find the cosine of C. So to do that, we are going to subtract A squared and B squared, and then divide everything by negative 2AB. So the cosine of C is A squared plus B squared minus C squared. When we divide by the negative, it's going to flip all of our signs by 2AB. When we plug in our results, cosine of C is equal to 9.47 squared plus 15.9 squared minus 21.1 squared all over 2 times 9.47 times 15.9. So the cosine of C is approximately negative 0.3410942, which tells us it is going to be obtuse because a negative cosine only occurs in quadrants 2 and 3, where the x-coordinates are negative. When we do the inverse cosine of our result, we get 109.9 degrees. Now that we know an angle, we can pull in either repeating the process to find angle B or angle A, or we can use the law of sines. So if we want to find Angle B, we can use sine of angle C over C, since that's the one we know, equals sine of angle B over B. So sine of angle C over 21.1, and angle C was that 109.1, 109.9, and that is going to equal the sine of angle B over 15.9. So the sine of B equals 15.9 times the sine of 109.9 degrees over 21.1. And then when you inverse sine this, or arc sine, you get B is approximately 45.1 degrees. And then doing 180 minus 45.1 and 109.9, A turns out to be about 25 degrees. And there we have all three angles and all three sides. So between the law of sines and the law of cosines, any combination of three pieces of information allows you to find the rest. All right, for this one, we're going to look at a roof truss. So we want to find angle B to the nearest degree for the truss shown in the picture. So we have side C, side A, and side B. So try this on your own and then check your answer after you've paused and played again. All right. So we know that we have a squared, b squared, and c squared. And if we're looking for b, then we want the version that has cosine of b in it. So b squared equals a squared plus c squared minus 2ac cosine of b. Again, rearranging, we get the cosine of b equals a squared plus c squared minus b squared over 2 times a times c. Again, that negative flipped all of the signs. So the cosine of b is equal to 11 squared plus 9 squared minus 6 squared over 2 times 11 times 9. And you can plug the result into inverse cosine, and you get b is approximately 33 degrees. All right, so when we're solving oblique triangles, these are triangles where none of the sides are the same. Then if we know one side and two angles, regardless of where that side lies, then we can find the remaining angle using the angle sum formula. That's the fact that they all add up to 180 degrees. And find the remaining sides using the law of sines. And these are examples just like we did in 8.1. If you know two sides and one angle that is not between those two sides, so SSA, then we can find the angle using the law of sines, since we know two sides and an angle. We can then use the remaining angle using the angle sum formula, and then law of sines again to find the remaining side. This one, remember, be careful if you have two triangles that exist. Repeat steps 2 and 3 for these, for those cases like we did in 8.1. When you have two sides in the included angle, SAS, then you can find the third side using the law of cosines. Find the smaller of the two remaining angles using the law of sines. And then find the remaining angle using the angle sum formula. And then when you know all three sides, find the largest angle using the law of cosines. Find either of the remaining angles using the law of sines. And then find the remaining angle using the angle sum formula. So here we have all of the different possibilities of three pieces of information about a triangle. We have SAA, ASA, SSA, SAS, and SSS. The only one that does not work is if you have angle, 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 because that does not guarantee scale, only similarity. We can then extend this into what's called Heron's formula, and this is specific to area. So if a triangle has side lengths of A, B, and C with a semi-perimeter of S equals 1/2 times the sum of the three sides, then the area of the triangle is given by the formula area equals the square root of S times S minus A times S minus B times S minus C. Okay, so for this one, we need to do a little bit of a review of what a semi-perimeter is. So a semi-perimeter is going to be half the perimeter of the original triangle. So the distance as the crow flies from Los Angeles to New York is 2,451 miles. From New York to Montreal is 331 miles. And from Montreal back to Los Angeles is 2,427. What is the area of the triangular region having these three cities as vertices, ignoring the curvature of the Earth? So we're going to do a little rough sketch of a triangle here. We have LA to New York to Montreal. Okay, LA is 2,451 miles to New York, 331 miles to Montreal, and 2,427 miles from Montreal back to Los Angeles. And we want to find this entire area that would be encased by 3 airplanes flying simultaneously. So in order to use Heron's formula to find the area, and to avoid having to use the law of cosines to find an angle, splitting it, doing all of those things so that you can use the law of sines to then find the area, we can use Heron's formula. And all we need to do first is calculate the semi-perimeter, which is 1/2 of all three sides added together. So it's essentially the average of these sides, but not exact because it's only half and not 1/3. And when we plug this in, we get our semi-perimeter is 2,604.5. And then using Heron's formula, the area is the square root of 2,604.5 times the difference of that semi-perimeter with all of the different sides. So 2,604.5 minus LA to New York times minus the distance from New York to Montreal times, I'm running out of room, Montreal back to LA, and the square root of all of that. And we get it is approximately 401,700 square miles. These are more calculation-based formulas and useful formulas before excessive computers were a thing. And this comes from combining, having to find the cosine and then applying the law of sines in the area shortcut. If you're curious about where it comes from, there's a pretty good explanation in these slides on Schoology if you are so interested. It does involve a lot of the identities that we talked about in Chapter 7, like some double angle identities. But other than that, we'll probably do a little bit of this during block period. But using the formulas, I think, is going to be most important for now until I am back from tennis. All right, if you have any questions, you know the math teachers that you can go to for help. Other than that, you can start working on the 8.2 homework.